Now, next application of Gauss law, how to calculate electric field due to a uniformly charged conducting sphere. Whenever the word conducting is coming means the charge inside the region is 0. Only charge resides only on the outer surface of the conductor. Whenever conductor is given, the conductor, no charge resides inside the conductor. Only charge resides only on the outer surface of the conductor. Now it is a sphere and its radius is r, and surface charge density of sphere is sigma. Sigma is surface charge density. Sigma is surface charge density of sphere. Now I would like to find electric field intensity at a point P, which is at a distance smaller from the center of the sphere. Which is at a distance smaller from the center of the sphere. Then once again it will get three cases. One point is inside point, that is smaller is less than r. One point is outside, that is smaller is greater than r. A third point is on surface. On surface means smaller is equal to capital R. Smaller is equal to capital R. To find for inside point. For anything, what type of Gaussian surface we need? Sphere only. Then let's assume we need to draw a Gaussian sphere. Draw a Gaussian sphere of radius r. Sphere means, suppose if I consider this is at a distance r, if I'm drawing a Gaussian sphere of radius small r, then for that element, just now we have derived all the times we're deriving the derivation same way. That means it is a ds bar which is outward. Since it is a positive charge, electric field also outward. Then we can say that d phi is equal to EDS cos 0. Total flux equal to integral of EDS. Here electric field intensity is same at each and every point. That's why integral of ds. Therefore total flux is E into 4 pi r square. This expression you remember for any Gaussian sphere here. E equal phi equal to E into 4 pi r square. Now we will come to the first point. The first point is we need to calculate for smaller less than capital R. If smaller is less than capital R, that means as we know that no charge present inside the sphere. Therefore, what is the charge enclosed by the Gaussian cylinder? 0. Therefore, according to Gauss law, total flux equal to charge enclosed by epsilon naught, which will be equal to 0. Therefore, I can write E times of 4 pi r square equal to 0. Therefore, electric field intensity at inside point is 0. Electric field intensity at inside point is 0. All of you clear? Now, we'll go for the second one. Smaller is greater than capital R. That is for outside point. For outside point, if I'm writing Gaussian sphere, this blue region is the Gaussian sphere and whose radius is r. And we know just now we calculated flux as 4 pi small r square into E. 4 pi small r square into E. Now let's assume the total charge on the surface is Q. Therefore, we can consider that inside the Gaussian sphere the charge is Q. Therefore, I can write according to Gauss law, flux equal to charge enclosed by epsilon naught. That is, charge enclosed is capital Q by epsilon. As we know that flux is equal to how much? E times of 4 pi small r square equal to Q by epsilon naught. Therefore, electric field intensity is equal to 1 by 4 pi epsilon naught Q by r square. Here, capital Q is equal to surface charge density into surface area. For what surface area this charge is located? Only for radius of capital R square. That's why electric field for outside point we will get as sigma times of 4 pi capital R square divided by 4 pi epsilon naught into small r square, we'll get as sigma capital R square divided by small r square. Epsilon naught times of r square. Now, last is not, one is very, very important, on surface. On surface means small r is equal to capital. Then electric field intensity on surface is equal to 1 by 4 pi epsilon naught capital Q by capital R square, or else sigma by epsilon naught, which we have found for conducting sheet. Same result we'll get. Now, suppose if I'm drawing a graph between electric field intensity with variation of distance, variation of electric field intensity with distance. At r equal to 0, what is the electric field intensity? 0. Until small r is equal to capital R, electric field intensity is 0. That's why I'm not sure. At small r equal to capital R, we have electric field intensity. That means which is on surface. Electric field intensity at surface will be equal to small r equal to capital R. Later on, the field is decreasing exponentially. That means E proportional to 1 by r square. This is the graph. It's a graph between E versus R. Now, next one is field due to a uniformly charged non-conducting sphere. It is also similar to conducting only the variation will come at the inside point. Outside and on surface is same as the previous result. Only the variation will come for inside point. How the variation will come inside point means it is uniformly charged non-conducting. That means the charge is distributed at inside point. The charge is distributed at inside point. We have any gravitation like that, acceleration due to gravity. Similar cases only we can consider here. Now, first of all, we have issued a Gaussian sphere of radius r, and flux due to that Gaussian surface is phi equal to E into 4 pi r square, which is similar. Now, according to Gauss law, total flux equal to charge enclosed by epsilon. Here, charge enclosed, we are defining as a volume charge density. That is charge per unit volume. That is volume charge density into volume of Gaussian sphere. That is 4 by 3 pi small r cube divided by epsilon. Volume of Gaussian sphere is how much? This is volume of Gaussian sphere and its radius is small r. Therefore, volume is 4 by 3 r cube. Therefore, charge enclosed is rho times of 4 by 3 pi r cube by epsilon. Then we can write in next step E times of 4 pi small r square is equal to rho into 4 by 3 pi r cube by epsilon. And on cancellation of 4 pi and r square also, we will get electric field E is equal to at inside point rho r by 3 epsilon. That means at inside point, electric field is directly proportional to distance. That means at the center of the sphere, what is the electric field intensity? 0. As you're going on, electric field intensity will increases and it will be maximum on surface. Later on, definitely we know that it will decrease exponentially this way. Now, when you come across to the outside point, it is similar. The total flux is 4 pi r square into E. According to Gauss law, charging enclosed by epsilon naught, Q by epsilon naught. Then E into 4 pi r square into charge by epsilon naught. Now, what is the charge enclosed here? What does the charge enclosed means? Here, charge enclosed is equal to rho times of charge is enclosed up to the region of capital R only. Even though you are considering Gaussian sphere outside, but charge is enclosed up to the radius capital R. That's why 4 by 3 pi capital R cube. Therefore, electric field intensity is 1 by 4 pi epsilon naught rho times of 4 by 3 pi r cube divided by r squared. That's why 4 pi gets cancelled. That is rho capital R cube by 3 epsilon naught times of r squared. 3 epsilon naught times of r squared. Now on surface, we will get this one as small r equal to capital R, that is equal to rho capital R divided by 3 epsilon naught. Rho capital R by 3 epsilon naught. It is similar to the previous. Outside point derivation is same as the conducting. Only the variation is there we are using surface charge density, here we are using volume charge density. Then later, if you draw a graph between variation of E with distance. For inside point, just now I told to you, for inside point, it is directly proportional to R. For outside point, it is inversely proportional to R square. Then electric field at center is 0. That's why electric field intensity linearly increases till what point small r is equal to capital. Then where it is surface, electric field intensity on surface is maximum. Later on, field decrease exponentially, that is E proportional to 1 by r square. This is called rectangular hyperbola, inversely square of the distance. That's why E proportional to 1 by r square, that is rectangular hyperbola. This is the variation of electric field intensity with distance. Okay, thank you. This is completion of Gaussian applications, and whatever the Gaussian applications for rod and everything whatever we have discussed, all are 5 marks questions. Be careful.